Hello, everyone. Welcome to our webinar on how to ace the computer science and artificial intelligence entrance test. As you may know, the computer science and AI bachelor program at Neapolis University Pafos in Cyprus is supported by JetBrains, which also offers 15 cost of living scholarships for the program. So if you're planning to apply, acing the entrance test is the crucial step. The test itself consists of two parts, math and programming. And today, one of the program's professors will share valuable tips and strategies to help you succeed in the math portion. So, this is the kind of live stream that can help you with that quite a while. We'll cover today the programming part, the math part Today we'll cover the math part, and we'll cover the programming part in a separate session in January. So stay tuned for that. And before we get started, I'd like to remind you that if you have questions, then feel free to ask them. You can drop them in the chat during the presentation, and we'll address them in the end. And if you're watching the recording, then please write your questions in the comment section or just join our chats. I will share the links below. And now let me introduce our today's speaker. We are thrilled to have Andrey Smolensky, an assistant professor at Neapolis University Pafos, with us. Andrey holds a PhD in algebra and has over 10 years of teaching experience at both universities and high schools. Welcome, Andrey. The floor is yours.
So before we start discussing the problems that appeared on the test last year, let me just add a couple of words regarding the procedure. So Alena mistakenly said that it's the discussion of mathematical part, confused it a bit with the programming part, but actually it's a bit harder to distinguish between the two because they happen simultaneously, and it's up to participants to split the time between tasks in mathematics and in programming. And some of the tasks in mathematics can also be solved by writing a small program. So they actually can be combined. All right. So another thing I wanted to add is that this test we're discussing today is the first part of the admission process, because there is also the second part where we talk face-to-face with participants, again discussing some of the problems in mathematics and possibly programming. And for the second part, it's harder to get prepared because it happens in real time. So we shall focus on preparing for the first part of the admission process, namely for the test which is automatically checked and where you only have to submit the answer and not the solution. However, getting the solution is the interesting part. So let us discuss the approaches and the methods one should exploit through the particular problems. And we shall start with problem number 1, which appears to be the simplest one, as the numbering suggests. And it's in the field of geometry. And the problem is about a trapezoid ABCD with bases AD and BC. So they are parallel. And it so happens for this trapezoid that if you intersect its diagonal AC and BD, the point O, then the two triangles out of 4, which are formed by this splitting of the quadrilateral, namely the lower one AOD and the upper one BOC, has their areas ratio equal to 4. So the lower one is 4 times larger in area than the upper one. And the question is, given that we know that the length of the base AD is equal to 17 units, find the length of the side BC. Well, we shall start, of course, by, as usual in geometrical problems, by noting some of the properties of what we can say immediately about the points in question. So first of all, since AD and BC are parallel, we can certainly say that some angles are also equal in measure. So the left corner of the left angle of the lower triangle, which is called OAD, is equal in measure to the angle OCB, of course. And similarly, OBC equals ODA. Now, this means that these triangles AOD and BOC are not just placed inside this quadrilateral, but they are actually similar. And not only similar, we can actually calculate the ratio of similarity. And it, of course, equals the ratio of the length of the bases of these two triangles. So its ratio is, let's denote it by the letter K, is just the fraction AD over BC. Now, we know AD, and our goal is to find BC. So if we only knew K, then we would immediately see the answer. And we do have access to the ratio K because we know that if you have similar triangles with ratio K, then the areas relate as squares. So the ratio of areas is the square of the ratio, that is K squared, which equals to 4 by assumption. And from this, we conclude that K equals 2 and BC is just AD over 2, which gives a numerical answer of 8.5. It is one of the often happening question, what sort of answer are accepted in the automatically tested platform. And the numerical answers like 8.5 are okay. But also the system does accept some other forms of answers. All right, now let us look at the problem number 2, which dives a bit deeper into the topic of elementary number theory. And it goes as follows. So the teacher wrote the numbers from 1 to 7, the integers, on the board. And then someone else, Johnny, chose five out of those 7 numbers, took their product, and wrote the result. And the thing is, this product is such that it's impossible to definitely determine whether the sum of these 5 selected numbers was even or odd. So the question is, what is this product which satisfies this property? Well, taking 5 numbers out of 7 is essentially the same as taking 2 numbers which we do not include in this product. So it's easier to work with 2 numbers instead of 5. So let's pick these 2 numbers and call them x and y. And then we can express the product in terms of x and y. Because the product of all numbers from 1 to 7, which is called the factorial, 7 factorial, or 5040. And then if you don't want to include some of the numbers, namely x and y, then you just divide the total product by x and y. So the product we're working with is 5040 over xy. Now, the question is, if we don't know whether the sum of these 5 select numbers was even or odd, we shouldn't also be able to figure out whether the sum of these 2 numbers, x and y, which we do not include, is even or odd. In particular, we don't know what x and y are, because otherwise that would give us a complete answer. So among these numbers, which are product of x and y, there are only 2 options which can be presented as products of 2 numbers from 1 to 7 in 2 ways. Namely, there is 12, which can be presented as both 3 times 4 and 2 times 6. And there is also 6, which is 1 times 6 and 2 times 3. Of course, this can be noted directly by looking at the multiplication table, or you can just say that among the numbers from 1 to 7, only the numbers 4 and 6 are composite, and they are both products of two primes. So this also shows that there are no other numbers which are examples of this phenomena. So all other double products are unique. So you have any other double product, x, y, and in particular any other product of 5 numbers, then you can distinguish not just the oddity, but these two numbers completely. Now, we know that x and y are one of these pairs listed here. So the question is, which is it? And it's easy to distinguish because the assumption of the problem states that one cannot determine the oddity of the sum. Now, if you look at 1 plus 6 and 2 plus 3, that is the factors appearing in the decomposition of 6, then both sums are odd. And so this shouldn't be possible because it's impossible to determine definitely whether the sum is even or odd. So we see and conclude that the product must be 12. And so the product of the 5 other numbers should be 5040 over 12, which is equal to 420. This provides an answer. Of course, with enough computing power, this problem can be solved by just going over all the possible combinations. Not very hard to do, but easier in this case to just look closely at the problem at hand. All right, now let us go to problem number 3, which is in the realm of logic and combinatorics, more closely to combinatorics in this case. So the setup is classical. There is an island. There are two types of people: knights who always tell the truth, and knaves who always lie. And once the meeting was happening where 100 islanders gathered around a circular table. So essentially just 100 of inhabitants sitting along the circle. And each of the islanders states one of the two things. Either they say that my left neighbor and his left neighbor are both knaves, that is, they both tell lies all the time, or he says the same about his right neighbor and his second right neighbor. So either two people on the left are both lying, or both people on the right are lying. And the question is, what is the minimum number of knights that could have gathered around the table? Well, first of all, let's note that the assumption of this problem are, in a sense, local. They are localized to sequences of 5 people along the circle. Because the information given by a particular islander only pertains to 2 people on the left of him and 2 people on the right of him. So it is localized to a group of 5 people. So it's natural that we should consider a sequence of 5 islanders. So if we take any 5 consecutive islanders in this circle, one might note that among them there is at least one knight. Because indeed, if you assume the contrary, that they are all knaves, they all lie, then the central one would say the truth. Because both 2 persons to the left of him and 2 persons to the right of him would be knaves as well. So he would be telling the truth. We should make him not a knave, but a knight. So among any 5 consecutive islanders, there is at least one knight. So at this point, of course, we can get from this one of the estimates. Because if you just divide all 100 islanders into 20 non-overlapping group of 5 consecutive, so 5, the next 5, the next 5, and so on, there are 20 groups. They don't overlap. They don't share knights between them. And each of these 20 groups has at least one knight. So we conclude from this that there were at least 20 nights in total. This is an estimate. So if we want to show that this is actually the minimum number of nights that is possible, then we have to present an example of a configuration where this happens. And this is, of course, very simple to do because the first note that among the 5 islanders, one must be a knight, suggests such a configuration. Namely, you just put one knight followed by 4 knaves. Or you can, and then you just repeat this along the circle. Or you can do it very similarly, put one knight and 2 knaves to the left and to the right of him, and then form a circle out of 5, or actually 20. This instead of 5 should be 20. 20 such groups. Anyway, this provides indeed 20 knights as an existing configuration, which shows that this amount, which serves as the lower bound, is indeed achievable. So this is indeed the minimum number. All right. Next problem comes again from the field of combinatorics. And this one is actually the simplest one to solve on a computer. Because, yeah, let's look at it first and then shall discuss the possible computer solutions. So we're looking at 5-digit numbers. And it is such that each of the digits 2, 3, 5, and 7 appears at least once, and digits 0, 1, 4, 6, 8, and 9, so all the others, never appear. So basically, you can just go over all 90,000 5-digit numbers and be done with it. Easy to check all the possible configurations which do satisfy this assumption. Or alternatively, you can, of course, just look at all the possible combinations. So this one is really easy to solve on a computer, but on the other hand, it's equally easy to solve just by hand, because this is simple combinatorics. So the solution, of course, is to see what are the structure we are getting in the 5-digit numbers with these restrictions. So we must know that since we have 5 digits in total and 4 distinct digits must appear at least once, we conclude that one of them appears twice and the other 3 appear exactly once. The question now is how to count such possibilities. Well, choosing which digit to repeat can be done in 4 ways, because, well, you have to just choose which one. Then there are 5 factorial over 2 possible ordering of these numbers, because indeed we have 5 numbers. We can reorder them, right, in any possible order. There are 5 factorials of them. However, since 2 digits are equal among these 5, we can swap them without changing the number. So this means we should divide the number of possible permutations of 5 digits by 2 to get the number of possible orderings of these numbers, because they come in pairs. All right. Now, this means that in total, there are 4 times 5 factorial over 2, or with the same 240 such numbers. You first have 4 ways to choose which number to double, and then you look at the possible ordering of the resulting numbers. So again, just 240 such numbers. All right, now we're getting to a bit more complicated but still simple problems in number theory. This one requires one to know what the least common multiple of a pair of numbers is, and what are the basic properties of that. So it goes as follows. We have pairs of natural numbers A, B, and we look at the least common multiple of such pairs of numbers. And it so happens that this least common multiple, that is a number which is divisible by both and the smallest possible such is equal to 5 to the power 49 times 7 to the power 50. And the question is, how many such pairs AB exist? And of course, the pairs are ordered. So a pair AB and a pair BA are considered distinct. This is an important distinction. So when you are doing these problems in your entrance test, pay attention to the details and to technicalities. All right, now to the solution. Well, first of all, we know what the divisors of the number 5 to the power 49 times 7 to the power 50 look like, because this is the decomposition of a given number into prime factors. So the divisors must also be of a similar form. So A must be 5 to some power, let's call it x, times 7 to some power, let's call it y. And same for B, which can be decomposed as 5 to the power 7 times 5 to the power s times s, 5 to the power s times 7 to the power t, where x, y, s, and t are some non-negative integers. However, they are not just divisors of 5 to the power 49 and 7 to the power 50, but this number is their least common multiple. So actually, the least common multiple of two numbers in the decomposition or given by their decomposition into primes can be presented as a product of the same primes to the powers which are maximal of the exponents appearing in the decomposition of these numbers a and b. So here in particular, the power of 5, which must appear in the least common multiple, is 49, and it should be the maximum of the exponent with which 5 comes into the composition of a and b. So the maximum of x and s must be 49, and similarly, the maximum of the exponent for the 7, namely y and t, must be equal to 50. So let's count such pairs of x, y, s, and t, which is easy to be done. Namely, if in the pair xs, at least one number must be equal to 49, because otherwise the maximum is not 49. And there are 50 pairs where x equals 49. Namely, you just go for x equals 49 and s going from 0 to 49 inclusively. And also 50 pairs where s equals 49 and x goes from 0 to 49. So there is a catch, however, that we have counted the pair 49, 49 twice. So actually, there are 50 plus 50 minus 1, that is 99 such pairs, XS. But we are interested not in the pairs XS, but in the pairs AB. So we should also count the pairs YT, which appear here. And it's done very similarly, and there is 101 suitable pairs YT. But since parameters x, s, y, and t are going independently, we can conclude that for any suitable pair of parameters x, s, you can append any suitable pair of parameters yt. So the total number is just the product of the numbers of suitable pairs. So it's 99 times 101, or 9,999 such pairs AP. Well, in this case, evaluating 5 to the power 49 times 7 to the power 50 on a computer, doing the complete expansion, and then going over all the possible natural number pairs AB with the corresponding least common multiple seems a bit excessive, if not impossible, because the least common multiple dealt here is really large. So if one tries to do it via a program, one really gets to first simplify the brute force approach, namely look at the possible divisors, which are products of powers of 5 and 7. But then once one simplifies to that, one is immediately drawn to the conclusion how to do it by hand. So indeed, one might try to do some of these problems via a program, face a difficulty, and then immediately switch to the purely mathematical solution, do it by hand. This is some phenomenon that we have seen in the participants in the last years. All right. Now let us look at problem number 6, which is a bit more advanced now. So we are coming to more complicated problems. So this one deals with polynomials, but in a very simple manner. So we are working with 3 real numbers a, b, and c, such that -1 and -2 are roots of a polynomial p of x of this prescribed form, x to the power 4 plus ax cubed minus 3x squared plus bx plus c. So this is the polynomial which depends on parameters a, b, and c. But if you substitute numbers -1 and -2, this expression gives you 0. So this provides some restrictions on the possible values of a, b, and c. And the question is to find the value of this polynomial, that is what will happen if you substitute 3 instead of x, at point 3. So how shall one approach this problem? Well, as I said, substitute -1 and -2 provides you some information about a, b, and c. So let's do that. And if you substitute -1, you simply get the value of 1 for x to the 4th minus a for ax cubed, minus 3 for minus 3x squared, minus b for bx, and c. So minus a minus b plus c and minus 2 must be equal to 0 because minus 2 is a root. All right, and similarly, if you substitute -2, you get that minus 8 times a minus 2 times b plus c plus 4 equals 0. On the other hand, what we want to figure out is the value at point 3, which evaluates to 27 times a plus 3 times b plus c plus 54. So how could one calculate this linear combination of a, b, and c, which appears in the value of p at point 3? Well, one simply know that one can actually take a suitable linear combination of the value at -1 and -2 to get something resembling very closely the expression at point 3. And it's easy to come with these coefficients because c comes with coefficient 1 in both the expression form the p at -1 and p at -2 and in the value at point 3. So if we manage somehow to express p of 3 as a linear combination of p of -1 and p of -2 plus some constant, then the coefficient must be of distinct sign and differ by 1 in absolute value. And then one can look at the coefficient relation between the coefficient, which would result in as b's being giving 3b in linear combination, and one quite fast finds that the suitable coefficients are 5 and -4, and then it just remains to check that indeed coefficient a behaves well enough. So one can say that one can indeed check that 27a plus 3b plus c is 5 times the expression on a, b, and c appearing in p at -1, -4 times the linear combination of a, b, and c appearing in the expression for p at -2. Now, of course, there are some constants. So we shall reconstruct the value of p at point 3. And we see that it's 5 times the value at -1 plus 2, because -a minus b plus c equals 2 according to the equation on the value of p at -1. And similarly, the expression with the coefficient -4 appears to be equal to -4, because you see in the expression for p at -2 you get the sum and +4 in the end. So it when moved to the right hand side, it gives you -4. And then there is a constant 54 in the expression p of 3. So in total, when you just add them together, you get the value of 80, and this gives you the final result. All right. Now let's get back to geometry again. This problem is a bit more complicated. Well, we are nearing towards the last part of the entrance test, so the problems naturally get more complicated. Still not terribly complicated. So this one goes as follows. We have a rectangle, A, B, C, and D, and a straight line, let's call it L, which intersects two adjacent sides of this rectangle, AD and CD. And the thing is, we know the distances from points A, B, and C to this line L. So the length of perpendiculars drawn from A, B, and C to this line L, and they are 7, 21, and 5 respectively. Obviously, this provides a rigid configuration. So in principle, this determines the distance from D to L. So the question naturally is to determine what it is, to calculate it. All right, so first of all, since we are working with distances, which are length of certain segments, let's draw these segments, and let's call the points of intersections of them with the line L, HA, HB, HC, and HD respectively. Now, it's very natural to know that the figure ACHCHA is a trapezoid with bases AHA, ECHC. So we know the two bases, the length of the bases of this trapezoid. So we should also look at its other sides. And one of the sides is the diagonal of our quadrilateral. And where's one diagonal of a quadrilateral, then there's also another. So let us introduce both of these diagonals and their intersection, the point O. Now, of course, since we're working with the projections, the perpendiculars from distinct points of interest to the line L, let's also introduce the perpendicular from O to L, and let's call the intersection point HO. So, as we said, this AHA-HCC is a right trapezoid with bases AHA and CHC, of which the length unknown. Now, since ABCD is a rectangle, the point O is a midpoint of this diagonal AC. And so the line OHO is the midline of this trapezoid because it happens to intersect as a side right in the middle, and it's also parallel to the bases. So naturally, the midline has its length just the mean of the length of the bases, which in this case is the length of AHA and CHC, which are 7 and 5 respectively, and divided by 2. So we immediately calculate that it equals 6. All right, it remains to just do some additional construction on this drawing. And one of interest is the line connecting B and HD, the projection of D onto L. So let's draw it, and let's also intersect it with the line passing through O and HO. And let's call this point X. Now, The thing about the point X is that it's again a midline of some triangle. Namely, note that the point O is the middle point of the diagonal BD. And it's also parallel to the line DHD. So the base of a triangle DBHD. So it's its midpoint. Now, on the other hand, the segment XHO is the midline of another triangle, namely BHDHB. Now, this means that we can effectively, at this point, calculate the length of the segment DHD, because it's twice the length of the midline of the corresponding triangle, which is XO. But the length of XO is just the difference of length of the segment XHO and the segment OHO. Because if you unite the non-intersecting segments XO and OHO, you get XHO. Now, if you try to expand this twice the difference, you'll get twice the length of XHO, but again, we noted that XHO is a midline of another triangle. So twice this length is the length of the base, which is BHB. And on the other hand, we already know the length of OHO. So we just have to multiply it by 2 again, despite having divided by 2 previously. So anyway, we know that this is just 21 minus 12, and it equals 9. So this makes the complete solution. Of course, this requires some additional constructions to solve. And you can actually brute force this problem by just expressing everything in coordinates, just plowing through all of the constructions. Doing it in coordinates is a bit complicated, but certainly feasible and very straightforward. And since you are allowed to use computer algebra system and advanced calculators, this poses no essential problem. All right, now let us get again to some combinatorics through the means of problem number 8, which goes as follows. So Alice and Bob, 2 players, are playing a game where they have 125 identical cubic chests and 27,000 coins. So Alice puts coins somehow in some fashion into these chests, maybe leaving some of them empty. And then she arranges them into a large cube measuring 5 times 5 times 5. So she stacks 5 of these cubical chests, one on top of another, and then she draws 25 such stacks together, forming a large cube. And Bob knows all the information about how the coins are placed into the chests, and he can now pick up any 2 by 2 by 2 subcube. So nearing cube. So he picks 8 chests, which are located in a 2 by 2 by 2 block. So not distributed somehow separately across this large cube, but sitting next to each other. And he can take all the coins which are contained in these 8 chests. So the question is, what is the maximum number of coins which Bob can guarantee to collect? So Alice has the freedom to distribute these coins in any fashion as she likes. The question is how many. So she tries, in essence, to make so that Bob cannot collect as many coins as he would like to. but there is a lower limit to how small this number can be. This is the maximum number of coin Bob can guarantee to collect, regardless of how Alice placed them. All right, so we shall solve this problem by first looking at some natural configuration related to 2 by 2 by 2 blocks. Namely, let's just look at this large 5 by 5 by 5 mega cube, and let's divide it to sections as follows. So first of all, slice one layer from the top, one layer from one of the sides, from the right in this picture, and one block up front, and then divide the remaining in half in all of three directions, and divide the slices as well accordingly. So how many sections do we have here? So first of all, we have 8 2 by 2 by 2 groups. Those are the groups which are hidden in this picture. So on the other hand, you have 12 2 by 2 by 1 blocks, namely the blocks you have in the front face, the groups you see in the right side face, and the groups you see in the top face. Also, along the edges visible, you see that there are 6 2 by 1 by 1 block groups, and just one 1 by 1 by 1 group in the corner closest to us. So you see that there are 27 groups in total, and we have 27,000 coins. So one of the variation of the pigeonhole principle, or the Dirichlet principle as it's also known, states that at least one of these groups contains at least 1,000 coins, because there are 20. Because naturally, if you have less than 1,000 coins in all of 27 groups in each of them, then there is less than 27,000 coins in total, which contradicts the assumption of the problem. So at least one of them contains 1,000 coins. So naturally, this means that Bob can guarantee to get at least 1,000 coins by just taking a 2 by 2 by 2 group which covers one of these 27 groups. So either one of these 8 which are 2 by 2 by 2 already, or something which includes these smaller groups. So the question is, can he do better, or is there a placement of coins into chests such that Bob cannot get any better than 1,000 coins? And again, it's rather obvious how to construct one. You just place 1,000 coins into a chest with all three coordinates odd, that is 1, 3, and 5. So in the corner, in the middle of the edges, and in the middle of the faces, and one in the middle, in the center of the cube, of this large 5 by 5 by 5 cube. And if you count accurately, you see that there are 27 such chests. So you actually can distribute coins in this fashion. But the distance between any of these two chests is already 2. So they do not fit into a single 2 by 2 by 2 group. So whichever 2 by 2 by 2 group you take, it only contains one of these chests. And so it only contains 1,000 coins. So this means that we can actually Alice can actually place coins in such a way that one gets exactly 1,000 coins, regardless of which group of 2 by 2 by 2 Bob takes. So this provides us with the answer that the maximum number of coins Bob can guarantee to collect is 1,000. All right. Now a problem with a bit more calculus flavor. which is about a certain parabola and minimization. So we are looking at the graph of the function, which is given by the equation y equals x squared minus 3x plus 5, a parabola. And we are taking 2 points on this parabola with the x coordinates 2 and 9 respectively. Let's call these points A and B. And then one picks another point called P, somewhere with, again, on this parabola, somewhere between points A and B. So some point on the parabola with the x coordinate P between 2 and 9. So as you can see in this picture, the segments AP and BP form two distinct regions together with this parabola. So you see that there is a narrow gap between the segment AP and the graph of this parabola, and the same with the segment BP. And the question is, if you try to minimize the sum of these areas, what is the value of the parameter P, which actually gives you the minimum sum of areas? Now, first of all, let's calculate what we know already. The ordinates, the y coordinates of A, B, and P are 3, 59, and P squared minus 3P plus 5, respectively. This is just done by substituting 2, 9, and P into this first equation, y equals x squared minus 3x plus 5. So the next question, how do we actually minimize this area? Because the area looks a bit complicated. Well, the thing is, we don't actually want to calculate the minimal area. We just want to figure out what is the parameter P, which gives us the minimum. So if we minimize something simpler, which attains minimum at the same value of the parameter, this makes the problem simpler. But what can we change without changing the minimizing value? Well, one approach is to look for some constant addition. And here, naturally, the area under the curve, under this parabola, is of course constant because we are not changing the parabola. So naturally, let's just put some perpendiculars from points A and B to the x-axis, and know that the minimum area of these narrow gaps is attained at the same parameter, which gives the minimum sum of area for these two trapezoids, which have AP and BP as one of its sides. Other sides live in the x-axis, and the bases are just these perpendiculars. So finding the minimum value for P for the original problem is the same as minimizing the sum of the areas of these two trapezoids. So let's just write down the sum of the areas of these trapezoids. It's very simple. To find the area of a trapezoid, you should just take the half sum of the basis length, which is just the length of the midline, and those in this case are just the y coordinates of points A, P, and B, so 3, 5, and P squared minus 3P plus 5, as we have figured out. And then you multiply it by the height of this trapezoid. Now, the height of the trapezoid in this case, since it's sort of lying on its side, is the distance between the x coordinates of the points A and P in one case and P and B in another case. So naturally, we just say, okay, the height of the trapezoid with the side AP is P minus 2. Well, the sum of the length of the bases is 3, which is the distance from A to x-axis, and P squared minus 3P plus 5, which is the distance from the point P. and you divide it by 2. And then you do the same for the second trapezoid with the side BP, which has the height 9 minus p, because this is the difference of x coordinates of points B and P, which are 9 and P. And then you do the same calculation for the half sum of the basis length. So when you expand all of this and simplify, you see that cubes cancel out, p squared times p squared here, and minus p times p squared here. So you are left with a quadratic polynomial. And the question now is to just find the value of p, which minimizes the quadratic polynomial 7p squared minus 77p plus 560 all over 2, but doesn't matter. This, of course, is achieved at the point 77 over 14, or numerically 5.5. So this gives the minimum for the original problem of minimizing the sum of the areas of these narrow gaps between the parabola and the two line segments. All right, now we are looking at the last problem of this collection, problem number 10, which is again from combinatorics. And it goes as follows. So we have a group of exactly n individuals where n is unknown yet. And there is a friendship relationship between some of them. Some of the people in this group are friends with each other, and for the sake of simplicity, friendship is considered to be mutual in this problem. And the following is known. First of all, each student has exactly 22 friends. Second, that any two students who are friends have no friends in common. And the third property is that if you have two students who are not friends, they have exactly 6 friends in common. And the claim of this problem is that this actually determines the value n uniquely. And the question is to find this value of n. Well, of course, this problem naturally prompts itself as a problem about graphs. So let us reinterpret this as a problem of graphs. So naturally, the vertices of our graph will be students, and will be joined by an edge if they are friends. So let's figure out what we know about this graph. Well, first of all, property number 2 implies that there are no triangles in this graph. A triangle is, of course, a collection of 3 vertices which are all joined by edges. There are no triangles here because indeed property number 2 says that if we have 2 vertices which are joined by an edge, that is students being friends, they have no other vertex to which they're both connected. So there are no triangles. So the particular property of this graph is that it has a lot of sort of V triplets. That is triplets of vertices which are connected by exactly 2 edges. So they are forming sort of a letter V among them. So if this is such a prevalent substructure in this graph, let's just count how many such triplets there are. And let's call them V triplets. So there are actually 2 ways to count this quantity. One way is to look at any pair of non-adjacent vertices. That is, non-adjacent means not connected by an edge. Now, if you have 2 vertices which are not connected by an edge, then this corresponds to 2 students which are not friends, and they have exactly 6 friends in common. So they are not connected, but they are connected simultaneously to 6 other vertices, which means that any pair of non-adjacent vertices is included in precisely 6 triplets. But on the other hand, each V triplets, each of the V triplets only contains one pair of non-adjacent vertices, because there are three pairs of vertices in a V triplet, but two of these pairs are connected, and only one is not. So this means that the number of our V triplets is 6 times the number of non-adjacent vertices in the graph. Now, on the other hand, we can look also at a pair of adjacent vertices, and we can count in how many V triplets it is contained. And the answer is there are 42 such V triplets. Because again, there is one property which we haven't yet used, namely property number 1, that each student has exactly 22 friends, which says that there are 21 additional edges from each vertex. So we have two vertices, and each of them has, so they are connected, and each has 21 more edges going to some other vertices. But since there are no triangles, this means that 21 edges going from the first vertex and 21 edges going from another vertex are going to distinct vertices. So in particular, they are not shared, which means that we can just add this 21 on for the one vertex and 21 for another and get 42 V triplets. Now, on the other hand, contrary to what happened for the pair of non-adjacent vertices, each V triplet contains two pairs of adjacent vertices. Again, by looking at what a V triplet is. So this means that the number of triplets, on the other hand, is 42 times the number of adjacent pairs of adjacent vertices, but divided by 2, which is 21 times the number of adjacent vertices. So we see, on the other hand, that we can count the number of pairs of adjacent vertices, because it's just the number of edges, because an edge contains precisely two adjacent vertices. That is the definition. But the number of edges is also known, because we have n vertices. We have 22 edges for each vertex, again, according to property number 1. And we shall divide it by 2, because each edge is counted twice if we do it directly, because it comes from two vertices. So in total, the number of pairs of adjacent vertices is 11 times n, the number of vertices. However, this means also that immediately we know the number of pairs of non-adjacent vertices, because everything else is non-adjacent. So the number of non-adjacent vertices, of course, the number of possible pairs in total, which is n times n minus 1 over 2. And just the way of pick two vertices out of n, and then you just subtract n. So we get the following equation. We see that 6 times the number of pairs of non-adjacent vertices, which, as we know, is the number of V triplets, must be equal to 21 times the number of pairs of adjacent vertices, which, as we have just calculated, is 11 times n. So we get this sort of equation. Now, obviously, every term here is divisible by n, and then you can divide both sides by 3, and you're left with n minus 1 minus 22 equals 77. Transfer all the constant to the right-hand side, you get the answer of n equal 100. And this provides a complete solution for problem number 10. All right, this was all the 10 problems in mathematics that we had in this test. So I guess we can finish my part on that. And if you have any questions, you're more than welcome to ask them.
Yeah, thank you so much for the presentation. Before we move to the questions, I'd like to remind our viewers that if you have questions, please drop them in the chat or in the comments if you're looking the recording, watching the recording. And we have several questions. I'll start. Can we solve mathematical problems using programming?
Yes, as I said, you do. It's only helpful in some situations where you can do a bit of a brute force. With a more sort of nuanced programming, you are likely to spend more time on writing a program than actually solving it by hand. However, one can use programming as an advanced calculator. So this certainly is allowed because we are trying to teach computer science students. So why not allow them to use a computer? That would be ridiculous trying to eliminate use of computers by computer science students.
Yeah, that makes sense. Okay. Next question is, how many times can we submit an answer?
If I recall correctly, there was no limit on the number of attempts at the mathematical part. It might change in the future. It might, in principle, depend on the particular problem, although unlikely to happen. Last year, if I recall correctly, there were infinitely many attempts, but it's hard. You will spend more. So, some students tried to brute force and to submit all possible values of the answer to just hit the correct value at some point. Well, while the test is automatically checked, we do see such a behavior in the system. Also, some of the answers, as you have seen, are not integer, so very hard to guess. But otherwise, assuming that students are doing their attempts honestly, which we would like to believe, yeah, no restrictions, especially since the answers are not assumed to be integers. There might be issues with formatting. Either you're using a decimal point or decimal comma. There might be minor issues of this sort or misprints. So we think that this should not be a problem in the time limited test. So no limit on the number of attempts.
Okay. Let's move on. Can I pass the entrance test online?
It's only online. It's done on a platform called Cognitera with automatically checked solutions. So you go on specially designed website. You are given all of these problems. You submit your answers via an online form, and I'm not sure whether you see whether your answer is correct or not immediately. Should be so
Yeah,
for the programming
you
part.
can check it. You can check it right online. I will share the link, so you can just try to fill in with the answers that we already discussed today, and you will see the answer if it is correct or not at the moment right online.
Yeah, certainly helpful to familiarize yourself with the platform because actually in some of the courses we teach to our students, we use this platform as well. So, and I guess at other universities they tend to do it more and more often these days. So if you know this platform, Cognitera, certainly helpful to be familiar with it.
Okay, let's move on. Could you please provide any preparatory resources besides the Youth Math Club?
Uh, I mean, those problems which happen here quite common. So you can go to any website which deals with this sort of problems, say brilliant.org, or you can take any classical books on training. Uh, I don't think there is some specific source for these types of problems. Actually, I believe most of them can be solved by someone who just studied well in high school. So I'm not sure there exists specifically designed preparation material. But I guess closer to the point, we might share some additional links.
You can find some materials at our landing page that I shared in the beginning of the live stream. There is a huge FAQ section, and there is a question named "How do I prepare for the entrance exam?" And there are some links to the preparatory materials, so you can take a look at that. And our time ran out, so I guess that that will be it for today. But if you still have any questions, feel free to join our chats in both WhatsApp and Telegram, and to meet our students and professors. And thank you for being here today with us. Thank you, Andrey, for joining us. And bye, everyone.
Yeah, my pleasure. Bye.